So the first algorithm we look at for doing this is local outlier factor is a very popular one, and it's one of the ones in that plot. It's the last column in that plot. And it's quite similar to dbScan, actually. So we talked about dbScan last week. We're using this idea. Oh, it didn't reset. Oh, I forgot that part. Okay. I fixed this part, but I didn't fix that part. The idea is you set up a neighborhood. So like remember in dbScan, we set a neighborhood around every point, and we say if there's this many points near you, then you're in the kind of core neighborhood, and any points that are within a given distance, but they're not dense enough, they're kind of this outside neighborhood, and then data points that don't have any nearby neighbors at all are outliers, right? So you can use that same idea to basically build a clustering, like anomaly detection algorithm. We set a neighborhood size, and did I have? Yeah, okay. And then for every neighborhood size, for every point, you're trying to basically determine how many points are near it, and he does this score thing. So let me go to the page. I didn't have time to come up with, like, make an explanation and make the slides. So on the Wikipedia page for this algorithm, they show it very nicely. So I was just going to re-describe this, but we can just show it. It's similar to that dbScan idea, right? So for every data point, you've got, if you're data point A, you look at all the points that are within a defined neighborhood, right? And you count how many there are, and then you use that to come up with this reachability score. So the main difference with dbScan is they say find all the distances in that area and basically pick the largest distance. So dbScan said, you know, find this many neighbors around me, and if I've got 3 neighbors within a distance of 5, then those are my core neighbors, and we're all core, we're in the same group, right? This one comes up with a number instead, right? So it says, can you reach A from B? It looks at the distance between them. So are they within this, is K at least A's, are A and B at least K neighbors of each other, right? So if K is 3, then you say, like, is B less, like, are there K other neighbors closer to A than B? That's how we say it, right? So if K equals 3, then A has, its closest neighbors are at this point B and C. So this B and C are all close neighbors of A, and so B is a close neighbor. And then you take the distance of them and use that as your distance, right? So they're taking either the max of the distance itself or K. Right, so you're basically saying, you know, you can have K neighbors, so in our default algorithm is saying pick 20 most of the time. From your 20 neighbors, your distance to that neighbor is either your actual distance to that point or your distance to the 20th neighbor, the furthest 20th one. So for any data point that's further than 20 away, the distance is just going to be set as the distance to your furthest K neighbor, right? So anyways, you come up with a score for between some points, and it means that the distances between ones that aren't your neighbors are just all equal. And then what you're trying to do is you build a classifier that says when we're looking at individual points, we can figure out whether they're neighbors or not, and basically make a cut for which ones are outliers and which ones are normal, right? So for every data point, you can compute this K neighbor distance to other points around them, and as long as they're under the threshold, then you say they're in the same set, and if they're further away, then it's positive. It's an outlier. Right, so all the ones where this score, I guess it gets normalized, right? There's different versions of it. So in some versions they normalize it, and that gives us this this better metric where basically if the LOF score is above 1, then you can basically consider it an outlier. and when it's below 1, it means at least it's got lots of neighbors and it's well-defined. And so then you get structures like this where points that have a low enough score become their own clusters, and all these guys defined as outliers. So using the same idea we had in dbScan, but explicitly building it for an anomaly detector. So this algorithm can be modified to be online. So the original point of that is offline. You take all the data points and you compute these distances amongst each other. But you can make it incremental. So there's paper link at the end where they do that. And you just update these density scores when a new data point arrives. You basically find all the neighbors that it affects and you update their density scores. And any data point that's further away doesn't need to be updated because it's always this max of like your furthest neighbor. So it's a bit more modular than something like k-means, because your score for every point is only based on your actual neighbors. So it's not too hard to make that one. Online. So then some other smaller methods. These two aren't used as often, but kernel density estimation. I don't have this one described in any detail at all. We mentioned it in our paper, that's why I put it on the slide. But essentially, you learn a kernel. So essentially applying, I think it's using like an SVM type kernel, RBF kernel estimation type thing. And if data points are outside the high expectation kind of classes, then you'd make them anomalies. But I'm going to explain one class SVM at the end, and that probably is more similar to this. So we'll come back to that. Oh, right, and this one uses, this was the other one that was on that plot with all the four methods. The one that looked more like k-means, right? Because it's essentially doing, this one does PCA on the data, and then uses those dimensions to basically come up with a threshold that says these points should be anomalous or not, right? Because if you did PCA and picked the first few principal components, right, you could compute kind of the distance of a point. When you project a point into the PCA space, you could compute the distance for every point along those new dimensions, just saying how far are you from the axis of the new data points, right? So if you think of your cloud of points has some kind of structure in a high dimensional space, right? But it's kind of at a direction. Your first principal component might be this dimension, right? And so your distance from this is kind of your deviation from that dimension, right? And your second principal component would be this one. So you could compute all these distances and say, what is, your distance from these axes to give you kind of a score. And so you can do that. And I guess the other oversampling, so putting more weight on that point so that the signal comes out more strongly is what the oversampling does. But it's kind of a simple method that essentially gives you like really an oval of like normality around some direction. And if your point's far outside that, it would work. But if your data isn't distributed as some kind of ovoid, it's going to be limited. So, but it's a quick and dirty kind of thing that you can do. Okay, so that's these ones. Yeah. Sure, yeah.
Sorry,
other questions?
Can you go back to that slide again?
Sure.
Sorry, can you clarify what it means by if the principal direction deviates significantly, the point is considered to be anomalous? I don't quite understand what you mean by that.
I'm trying to see anything else that says how it's different to what I said. The principal direction.
So like here in your image, right? So
yeah.
you have like this cloud, this oval cloud of data, right?
Yeah.
You have the principal axes P1 and P2, right?
Yeah.
And then so if you calculate the x that's down by like the horizontal axis, right?
Yeah.
How would the direction of that x kind of differ from one of the other data points that are inside?
Sorry, I clicked on something here. trying to get that back. Yeah, so what it's more about the oversampling part. I'm trying to remember what that meant. So say we're trying to figure out this point, right? And figure out whether it's there or not. So what we're saying with the oversampling is that we add kind of, many versions of this, like of this point into the data set so that it comes out has more of an impact. So put many different versions of, like, copies of this into the data set and then run PCA again. And so this would shift the PCA kind of main direction by a little bit, right? And so you're trying to see the impact of this data point, because you're right, you have to have some different, right? What's deviating? It's not really just this distance from here. It's like, well, how much? I guess that's a different method where you're looking at the difference from the axis. How much is adding this point changing what that principal component would be if you had a lot of them? And you can use that as a measure of how off the axis that is, right? So instead of just computing this distance, I guess that would really just be variance. You could basically oversample the point, run PCA, and then you'd use this change in the axis to be the measure. Does that make sense?
Yeah. So that makes sense.
Yeah.
How do you know how much you should oversample it to give it a strong enough weight?
I don't know. You have to read into that field. It's like a whole method. So obviously, yeah, it's a tunable thing, right? So the size of n here is going to make a big difference. How many is enough? And you probably could do like a statistical kind of measure, like even a Hufting bound or something, and say, like, if you have this many data points, it's going to give you this confidence. But it's yeah, that would be dependent on which way you're doing this.